Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. I have owned a standard RF Explorer for a few years now, but never really dug into the thing to understand how it did what it did. When I received my new RF Explorer Plus for Christmas, way cool, as an inquisitive experimenter, I started getting curious about how it does what it does and how to use it more effectively. I'm assuming that others would like to have this same understanding that I now have, and so I'm sharing it with you all. In this video, I'm going to explain what you're actually seeing on the screen and how to have more predictable results. This is all possible when you understand how it does what it does. If you have questions or comments, please feel free to add a comment to this video. I make a concerted effort to respond to every comment. If you find this video helpful, please click on the like and subscribe to the channel. Don't forget to subscribe. Let's dive into the background of how this thing works. In order to understand how the RF Explorer works, we have to back up a little bit to see the bigger picture. We need to talk briefly about time domain versus frequency domain. There is the time domain, which is the place where we live. We experience life as time passes by. Then there is the frequency domain. This is where the spectrum analyzer lives, giving us information about the frequency content of what it hears. For more complete discussion on this subject, see my video on the topic. I've put a link to it in the upper corner of the screen here. So how does the RF Explorer get the data that we see on the screen? To begin with, the RF Explorer has a front end. I'm not going to get into the RF front end. We'll just say that it's got stuff up front between the input connector and the rest of the stuff over here. It gets its data by using an analog to digital converter to sample the stuff that it hears from the front end in the time domain. That is to say, it records the amplitude of what it is hearing in discrete steps of time. So for instance, at time equals 0 seconds, the amplitude might be 0.1 volts. At time equals 1 nanosecond, the amplitude is 0.12 volts, and so on and so forth. Regular, discrete steps of time. It is a continuous stream of time domain data that it provides to the internal microcontroller. However, the RF Explorer displays data in the frequency domain. So how does the RF Explorer get this sampled time domain data transformed into the frequency domain so it can put it on the screen for us? It uses an FFT. Okay, so I just used a 3-letter acronym, or TLA, which you might have heard the term FFT before, but you don't necessarily know what it is. Well, here's a quick explanation. So what exactly is an FFT? It is a fast Fourier transform. Fast Fourier transform. Now the Fourier transform is the mathematical means to transform a signal from the time domain to the frequency domain if you know the mathematical equation used to describe it. Well, we don't have that. All we have is a bunch of data samples in the time domain. So in marches the discrete Fourier transform, which is the mathematical means used to transform sampled data like we have here in the time domain to the frequency domain. But the computing power necessary to complete a discrete Fourier transform is enormous and time-taking, and is way beyond what small devices like this could even dream of doing. In answer to this problem, some brilliant mathematician came up with a way to do it much more quickly, and the fast Fourier transform, or FFT, was born back in the mid-1960s. The input to the FFT is a number of discrete time domain samples which must be some power of 2 samples long. So you could have 2 samples, 4 samples, 8, 16, 32, 64, 128, keep on going, 40, 96, but it has to be a power of 2 samples long. And the output of the FFT are discrete frequency buckets. The width of each bucket depends on the parameters provided to the transform. For example, everything that looks like it is between 499.075 megahertz and 500.025 megahertz might go in the 500 megahertz bucket and is reported as being 500 megahertz. This gives us 50 kilohertz of resolution. Now, if you can picture this as a bin of miscellaneous hardware in the time domain samples from the ADC, and these little containers as the output buckets of the FFT. Our hardware FFT sorts out this hardware into 240, 440, 632, 832, 1032 screw sizes. Now, there's no real correlation between the number of output buckets and the number of samples that we put into it. We can put 512 time domain samples into the FFT and sort these out into 112 buckets. Now, let's turn our attention to the RF Explorer. The RF Explorer in its standalone mode gives us 112 frequency buckets, which we see on the screen. The width of these frequency buckets depends on the span of the frequencies we're looking at. The wider the span, the wider each bucket gets because we have a fixed number of buckets. Suppose a given bucket extents our 500 megahertz to 500.5 megahertz. The center frequency is 500.25 megahertz. Any device that uses an FFT to perform this task, including the RF Explorer, cannot know the difference between any signal lying within the confines of this bucket. So suppose we had a signal that was 500.1 megahertz. It would be reported as a 500.25 megahertz signal. If we had a 500.4 megahertz signal, it too would be reported as a 500.25 megahertz signal. The reason is that each of these frequencies reside in the same 500.25 megahertz bucket. Now let me show you this fact. With this demonstration, I'm going to slowly change the frequency of my signal generator, and you'll notice that the RF Explorer's reported frequency does not change until I drop over into the next bucket. Now you can see that I set up the center frequency at 500 megahertz. My span is 56 megahertz. And the number of points is set to the standard 112 points. You can see here my frequency that I'm set to is 500 megahertz. Notice the frequency that's being reported by the RF Explorer. Now watch as I change by tenths of a megahertz. Watch the readout on the RF Explorer. Up 0.1, nothing has changed. Up 0.2, still nothing has changed. 0.3, 0.4, 0.5, now it changed. 0.6, 0.7, 0.8, 0.9, 1 megahertz. One more, there it goes, it finally changed. So on and so forth. So you can see that the resolution of frequency is in these buckets. Here we are at 500 megahertz, Now, before we get too worried about the fact that I have a 500 megahertz signal and I have RF Explorers reporting 500.252, watch what happens when I change the span to 0.112, giving us far better resolution. Now that we understand this, let's see how these buckets are arranged on the screen so we better understand what we're seeing. It is true that the RF Explorer in standalone mode has a mere 112 frequency buckets. Now, horizontally speaking, the very first bucket is represented by the start frequency, and the very last bucket corresponds with the end or stop frequency. The very first and last buckets are actually a special case as buckets go, because these straddle the start and stop frequencies respectively. So the center of the bucket is right on the edge. So we have the start frequency, we have the first bucket, its center is right on the beginning here at the start frequency, and on the other end, the last bucket, bucket 112, its center straddles the end frequency, whatever it is that we have specified. Now, from a perspective of the screen that we see, they act kind of like half buckets, only because half of them exist beyond the edge of the screen. If all of the other buckets were 0.5 megahertz wide, these would appear to be 0.25 megahertz wide. The other 110 buckets are arranged between these two exceptions. Now, what about the frequency that is reported by the RF Explorer? The frequency that is reported for each bucket is the center frequency of the bucket. If the frequency of the lower extent of a given bucket is 472.25 megahertz, and the upper edge is 472.75 megahertz, then the data placed in that bucket is reported to have a frequency of 472.5 megahertz, because this is the center of this bucket. Now, because the two end buckets already straddle the start and stop frequencies, the frequencies reported for data in these buckets are the start and stop frequencies. Let me say that I've provided an Excel spreadsheet calculator for you to calculate this stuff. The link is in the description below. What I've been trying to describe to you on the board is this picture here. We have the screen extents. This is what you actually see on your screen. We have the start frequency over here. We have the stop frequency over here. And dead in the middle is the center frequency. We have 112 frequency buckets of the FFT. And notice that the first bucket is straddling the start frequency. So half of it is actually technically off the screen, and the other half of it is on the screen. So anything in here is going to be reported as the start frequency. Same thing with the stop bucket of 112. It straddles the stop frequency. So the center of the bucket is the stop frequency, and anything that is in here gets reported as the stop frequency. The other half of the bucket is off the screen. The other 110 buckets are between these two across the entire screen. Now, the more distance there is between the start and stop frequency, the wider these buckets have to get there, because we have a fixed number of buckets. The resolution or width of these buckets is determined, like I said, from the span and the fact that we have 112 buckets. And the frequencies that are reported are the center of each of these buckets. So what if we want to know what the resolution is given a set of circumstances, or we need to establish a particular resolution so that we get the kind of resolution we need for our measurement. Let's talk about situation number 1. We're out in the field and we don't know exactly where this frequency is. We don't know where this signal resides, but we know that it is somewhere between these two frequencies. So we know that we have to cover a particular span of frequencies to capture that signal. And we also know the number of sweep points because it's 112 for standalone mode as we're wandering around out in the field. And so we want to know how close the indicated frequency is to the real frequency. Well, we use this formula. The resolution, or the width of the frequency buckets that the FFT uses, is equal to the span of frequencies divided by the number of points minus 1. So let's look at an example here. We know, for instance, in our given situation, that this signal is somewhere in a span of 25 megahertz. And we know the number of sweep points is 112 because we are in standalone mode wandering around in a field somewheres. So we take out the equation. The resolution is equal to the span divided by the number of points minus 1. The span is 25 megahertz. Number of points is 112. We end up with 25 over 111. So the resolution is 0.2252 megahertz, which is the width of each frequency bucket. Well, there's another kind of a situation. We know the desired resolution. We know how close we want to be to the real frequency. And again, we know the sweep points because we're standalone. It's 112. There you go. And so what we want to do is know how to set up our RF Explorer so that we can get the resolution we want. And that is done through determining what the span needs to be for that particular measurement. Well, here's the formula that we use. We have the span that is required to achieve this desired resolution is equal to the resolution that we're trying to establish times the number of sweep points minus 1. So let's look at our example. Now, suppose we're out in the field and we want to make sure that the resolution of our measurement is within 0.1 megahertz. The number of sweep points is 112 because, again, we're in standalone mode. And so we break out our equation. The span is equal to the resolution times the number of points minus 1. So we have 0.1 megahertz times 112 minus 1, or 0.1 megahertz times 111, gives us a span of 11.1 megahertz. All right, so we have talked about resolution or bucket width. But what about this one? We want to know what frequencies the RF Explorer is going to report for each of these 112 buckets. Well, bucket 1 and bucket 112 are easy. That's the start frequency and the stop frequency. But what about all of the buckets in between? So that is what we're going to be looking at next. We already know the start frequency and we know the resolution. Either we calculated that or we determined that we required a particular resolution, and we want to know what frequencies the RF Explorer will report for each bucket. So we use this formula to find the frequency that the RF Explorer will report for each of its frequency buckets. The reported frequency for any given bucket N is equal to the start frequency plus the resolution times the bucket number N minus 1. Let's look at an example. First, we need to find the required span to achieve our desired resolution. We have determined that we needed to know the frequency within 0.5 megahertz. And we also know that we have 112 sweep points. So we break out the equations for resolution. From above, we calculate the necessary span, and that's 0.5 times 112 minus 1, or 0.5 times 111. That gives us a span of 55.5 megahertz. Next, we find the start frequency. Well, we know the center frequency is 500 megahertz because that's where we're at. And the required span we just calculated at 55.5 megahertz. So the start frequency is equal to the center frequency minus half of the span, or 500 megahertz minus 55.5 over 2, which gives us 472.25 megahertz. Finally, we can calculate the reported frequencies for each bucket. We just found the start frequency was 472.25. We already know the resolution because we specified this at 0.5 megahertz. And so we pull out our equation. Reported frequency for any particular bucket is equal to the start frequency plus the resolution times the bucket number minus 1. And notice that for bucket number 1, 1 minus 1 is 0 times 0.5, that's all 0. So the reported frequency for bucket number 1 is the start frequency of 472.25. For bucket number 2, we end up with 472.75, 473.25 megahertz, and then all the way down to bucket number 112, we end up with 527.75. Now, this should be the stop frequency if we did everything right. And the stop frequency is equal to the start frequency plus the span. So that's 472.25 plus 55.5 megahertz is equal to 527.75. Well, looky here. These are exactly the same. Now we've done the whole horizontal frequency thing. What about the amplitude? Well, the analog to digital converter provides a number which corresponds to the voltage that comes to it. And that goes to the processor. And these are the samples that go into the FFT and eventually end up in the frequency buckets that we've been talking about. Now, the processor knows what the conversion has to be between these numbers and the voltage that they represent. It also knows how to convert voltage to dBm. And so they are converted to the decibels with the standard RF world assumption that the impedance is going to be 50 ohms, and that is what we see on the screen. Well, theoretically, you now have at least a better understanding of your RF Explorer. The better understanding will help you use this wonderful instrument more effectively. If you found this video helpful, please click on the like and don't forget to subscribe to the channel. Thank you so much for watching. Until next time, Toodle-Oots.